I hope everyone's doing well. I am Mr. Ish. We're looking here at a very interesting infinite geometric series pattern that develops with regards to equilateral triangles. Equilateral triangle, 3 equal sides, 3 equal angles. The pattern develops with regards specifically to area. So before I show you the pattern, let's quickly determine the area of an equilateral triangle. If everything is with regards to a certain base all around, we're representing everything with regards to B. You have a certain height of this triangle. We're not using the basic formula half base times height because I want to differentiate it for equilateral triangle, because you can have a slightly different formula come about. Here's your height. You know you're going to have a height over here with respect to B, and you can do it. Tan 60 degrees is equal to H over, for this part right over here, I'm having a B over 2 because this base B has been split into half and then a B over 2. H over B over 2. What do I have over here? Tan 60 in terms of trigonometric ratio is equal to root 3. I'm solving for H. H is equal to root 3 times B over 2. And you have root 3 B over 2. Now I know H. I know area for triangle is equal to half base times height. I have here half base times this height, root 3 b over 2. When I solve it out, I have here root 3 b square over 4 is the area of an equilateral triangle, and let's push it aside. Let's talk about the pattern. Here is our starting equilateral triangle. We know the area of this is going to be this, and I'm going to write here the area of my very first equilateral triangle is going to be root 3 b square over 4. What is the pattern and how does it develop? Find the midpoints of each of these, and we are looking here at this. Now we're not looking at each of the 4 triangles that I've developed. My original triangle is split into 4 equilateral triangles. That's what they are. We're looking here at always this corner triangle right over here at this point. There'll always be a corner triangle. We're looking at that. My original triangle was this one right here, which I'm highlighting for you. My next triangle I'm focusing on is now this triangle right over here. This triangle area is going to be 1/4 of that entire, and this is my round number 2. I have root 3 b square over 4 times 1 over 4 in terms of the area of this triangle, because I've split the original by a factor of 1 over 4, and the triangle area of this one should be the original times 1 over 4. So you have that and you know that. So it's root 3 b square over 4 times 1 over 4. Now look right over here, let's do another split. When I split it, I've generated this other triangle, and that's what I'm focusing on. But everything has been split again into a bunch of other triangles, all equal. But this right here is my third round, and I'm focusing again here on this corner triangle. And the area of that would be root 3 b square over 4 times 1 over 4 times another 1 over 4. Because the original was split into 4, and that has been split again into another 4. Now we'll do another midpoint development here, and then develop another cut over there, and we can look here at again at this triangle right here. You can see that one is my 4th round triangle, and it'll be root 3 b square over 4 times 1 over 4 times 1 over 4 times 1 over 4. That's what the pattern is. Now we can do, in this limited space, I have another round over here, and then we can cut it, and we're looking here at this. That final amount, which I'll represent for you, my 5th round, it'll be root 3 b square over 4 times 1 over 4 times 1 over 4 times 1 over 4 times 1 over 4. And you can see an infinite representation develops, a geometric representation. In a clean aspect, this is what I'm looking at right over here. Without me doing all of these bold lines, you can see the pattern develops, and it looks something like this. You'll always have this corner triangle, which is 1/4 of the original triangle. The large one, then the next one, then the next one, the next one, and you can see it'll keep going on and on. And that right there is our infinite geometric pattern. So let's start consolidating some of these values. When I'm looking here at this original A1, I know the A1 area was just root 3 b square over 4. When I'm looking at A2, I'm doing the computation. I have a root 3 b square over, well, it's a 16. When I'm doing here in A3, the 3rd round, I have a root 3 b square over 64. When I'm doing the 4th round, I have here root 3 b square. You can simply just do 4 to the power 4, and you'll have 256. Then let's look at the 5th round. You know it's going to be root 3 b square over 4 to the power of 5, and that'll be 1024. Now you can see A6, A7, A8. These are your various rounds of areas of these corner triangles which you're always focusing on. They're always equilateral triangles, but they're always 1/4 of the area of the round before. So now let's start developing our geometric pattern. What will our pattern be? This is what it is. You have everything over here, and a common term always is what you're seeing here in the first one, root 3 b square over 4, and everything goes by a factor of 1 over 4 from there. my pattern can be represented as this. If you're saying n is equal to 0, your first round we're calling it from 0 up to infinity. I have root 3 b square over 4 times 1 over 4 to the power of n. When I'm doing n equals to 0, this becomes a 1, and I start here with my first. N equals 0, but my count will be here from 1. You have a little bit of an inconsistency here, but it's fine. There's nothing wrong with it. We understand n equals 0 represents my first item, then we go from there. This to the power of 0 becomes a 1, so you're just left with root 3 b square over 4. Then you'll always have a times 1 over 4 times 1 over 4, on and on and on. You'll see it'll go through. But this right here is our series rule, of which there's a constant. What is my constant? You can push this out. You can really say my rule is root 3 b square over 4. Then I'm looking at this, n is equal to 0 and up to infinity 1 over 4 to the power of n. When you're looking at this item over here, this right here is your common ratio. You can take any of these items, an item and then item before, you'll always see the ratio to be 1 over 4. In infinite geometric series, this item which you have over here is your common ratio, and it's a cheat. You can remember that. When the common ratio is less than 1, you know you're going to have a convergent infinite geometric series. And how can I determine my sum of this infinite geometric series? All of these corner equilateral triangles which are going here towards infinity in terms of their representation of the series from 0 to infinity, the infinite number of corner equilateral triangles, the sum of their areas can be easily represented by a1 over 1 minus r. What's my a1? My a1 is going to be exactly right here. When n is equal to 0, you end up with just this item, and this is what it is. And we'll have root 3 b square over 4 divided by 1 minus common ratio. 1 minus 1 over 4 is a 3 over 4. These can cancel out. The 4's will cancel out. You'll end up seeing you'll have a root 3 b square over 3. When you simplify this, you'll have a b square over a root 3, and this will represent the sum of all your equilateral triangles here in the corner as you're examining them, and that will be the total of your sum, and it'll make sense. When you look at this item over here which represents the sum of your infinite geometric series, and we can make it better for you right here, the sum of your infinite geometric series which represents the area of your corner equilateral triangles in an infinite geometric progression, that right there being your area. Eliminate this b square out. You're really looking at a 1 over root 3. That's what it is. B square is an item which counts in it, but I'm just talking about the validity of my end result. When I look here, root 3 over 4 plus root 3 over 16 plus root 3 over 64 plus root 3 over 256 plus root 3 over 1024, all of these values will slowly add up, creep up as you're adding infinite numbers to 1 over root 3, and you can see it. If I'm looking at 1 divided by root 3, it is equal to 0.57735. When I'm looking at root 3 over 4, I do root 3 divided by 4, I have 0.433. I'm away from that 0.577 value. Then I'm going to add root 3 over 16 plus 3 root divided by 16, and I've come up to 0.54. Then I'm going to add root 3 over 64 plus 3 root divided by 64, and I've come up to 0.568, but this value was 0.577. I'm still shy from it, I'm still away from it. Then I'll add plus root 3 over 256 plus square root 3 divided by 256, and I'm slowly coming up, but I'm 0.575. This is 0.577. And let's do root 3 over 1024 plus square root 3 over 1024, and I'm getting here 0.576. So it's good. It's actually showing me this result is good. As I start adding infinite number of these items in my progression, the sum of those items, or the sum of the series, will actually tend towards b square over root 3, and it will be equal to that. And you'll see the numerical aspect of this, pushing out the b square from all of that, will become closer and closer to this 1 over root 3. I've shown you that by calculator, and you can check it for yourself. But this result over here is good. You have an infinite geometric series here with regards to equilateral triangles, and you can see it. You're always focusing here on your corner triangle. The sum of those individual triangles from the large to the small, the next small, all of that will equal and tend towards b square over root 3. And that right there is the end of this video. Thank you.